Okay, so today's problem counting bits. I solved it like couple minutes ago, but the problem is that recording the video, I didn't turn on the headphones. So, explaining the approach. The first approach is just simple. I can convert the number I. So the idea of this problem, we have an sequence consecutive from 0 to n. And for the every number, it's like n complexity is like n can be 10 to the power of 4, like 10 to the power of 4. And so for every I should output the number of ones in the binary representation of I. So like for I0, I have all zeros, answer 0. For 1, I have only 0, 1, answer 1. For 2, I have 0, 1, 0, answer 1, number of bits. For 3, I have 0, 1, 1, so number 2. The result number of bits like 1 and 1. For the 4, I have 1, 0, 0 is gonna be number 1. For the 5, I have 1, 0, 1, so number of ones 2. For the 6, I have 1, 1, 0, so number of bits 2. And for the 7, number of bits, so I have 1, 1, 1, so number of bits 3. And I need to output this answer array. So the question is how to efficiently calculate this number of bits for this sequence. I can, for every number, I can convert the number for every I can convert a number to the binary representation of it and have an answer. And to convert the binary representation for the every like I gonna be log of I. So the sum of complexity of that one gonna be log of 0 plus 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 log of n, and there are n plus 1 element in the sum. So this sum can be used as the integral can be used as approximation for the sum. Um, um, so the integral gonna be x log x minus 1. I add the bounds from 0 to n plus 1, and then upper bound, lower bound gonna be x 0 by log x minus 1, so 0. Upper bound gonna be n plus 1, so n plus 1 plus multiplied by log n plus 1 minus 1. And this is approximately like this higher term multiplied by higher term gonna be n plus 1 by log n plus 1, or simply simplifying that to log n by n. So the time complexity of the first approach, when I convert every number to the binary representation and count the number of ones in the binary representation, is n log n. That's pretty much uh, satisfies our like condition of n 10 to the power of 4. Um, so like it's gonna be 10 to the power of 4 by log 10 to the power of 4. It's gonna be 4 by log 4, 10 by log 4, so like log 10. Um, and this one gonna be log 10 by log 2. So this is constant, so the result gonna be constant by um, log, let's say, log 4. Um, yeah, so it's uh, like not constant, but like 4 log 10. 4 log 10 squared uh, by log 2. So like roughly 10 to the power of 5 or like 10 to the power of 6. Um, this is the first approach. The second approach is actually using DP. So instead of like having this n log n, to calculate it in n time, often time. So I noticed this interesting pattern. When I shift by one, um, I can reuse the previously saved number of bits, and then I can recover this one or zero by comparing with ending with one. So let's say I want to calculate the number of ones in six. So for the first step, I shift its binary representation to, or like I shift I um, by one to the right. So I have, instead of 110, I have 011, and I need to jump and count and get the number of bits for 011. A number of bits for 011 gonna be 2, this one. And then it's basically the part number of bits, efficiently calculate the number of bits um, in the first half of the number. In order to get the number of bits in the second half, like the uh, lowest bit, I need to compare this I with one. So I need to do this I and one check. Yeah, and then I can add those two numbers, like number of bits for the I shifted by one to the right, plus I and one, is it like 0 and 1, and then gonna be like I and 1 gonna be 0 because the lowest bit is 0, and number of bits for the uh, higher higher bits is gonna be like 2. So the result is 2. Same, like different one answer is here. So the same highest bits here, 1 and 1. We calculate number of bits there, like 2. And then the lowest bit, I compare it to, like, I check 7 and 1, gonna be 1. So I add like 2 plus 1, gonna be 3. Yeah, and basically I explained it here. So for the 111, as example, for this example, I shift I by 1, and I get this one I. So this I gonna be, result gonna be, so I by 1, so it's 7 shifted by 1, gonna be what's that, 3, and the number of bits for the 3 gonna be 2. So dp of 3 gonna be 2. And then the second step, I need to do I and 1, and it's gonna be 7 and 1, and it's gonna be equal 1. So I add 2 plus 1, and the result, it's gonna be 3 for the number of bits in 7, in I equals 7. So next I'll program this, quite simple programming for the second approach. So I'll have the int dp array equals new int, and then n plus 1, and then dp of 0 equals 0. Then I'll do for int I equals 0, I less than or equal n I plus plus, and then dp of I equals dp of I shifted, so here from 1, shifted by 1, plus I and 1, and then I'm gonna return dp. So that's it. Yeah, that's it.